Vinicio Gómez. Vinicio is coming from the Facultad de Ciencias in UNAM, and he will be talking about ribbon graphs and the DNA reporter strand problem.
Thank you very much for the organizers. I am happy to be here in the CIMAT Mérida, and we begin. Right. Right. Well, a ribbon graph is a surface with boundary represented as the union of two sets of disks. One are the vertices and other are edges. The vertices and the edges intersect in disjoint line segments. Each such line segment lies in the boundary of precisely one vertex and precisely one edge. And every edge contains two such line segments. This is a ribbon graph. This is a vertex, and this is an edge. The one edge intersect a disk in one line segment, or includes in two line segments. Come on, please. The ribbon graphs are also known as thickened graph. Let G be a finite graph. A thickened graph is a compact orientable surface such that is topologically embedded as one complex as a deformation retract. The problem interesting now of the talk is I knew this in a talk of Natasha Chudkowska about topological models for studying DNA self-assembly at the seminar Geotop. She teaches us about the self-assembly process. I can recommend the Arthur Olson's video titled Self-Assembly Virus. In this video, she puts many pieces, shake the pot, and the pieces form a ball or something. This is impressive for me. And what I understand is the self-assembling is how the virus works, reproduce. Well, the new fact is through self-assembly of branched junction molecules, many different DNA structures, graph thinking of, can be assembled. This includes two-dimensional arrays, three-dimensional polyhedra, like cubes and octahedrons, and arbitrary spatial graph. The molecular construction of a graph is done such that the edges are represented as duplex DNA molecules, and the vertices are as branched junction molecules. This is an example of a DNA cube with 6 cyclic strands. Natasha shows a book. This is from open access. You can download it without problem. And she says very, very interesting things. There are new graphing variants. But for example, we can imagine the DNA self-assembly process like a molecular Lego of flexible tiles. Each tile is a branched junction molecule, and this can be represented as a vertex with half edges labeled with their sticky end types. In this must match. Not any arm of the molecule stage with another. Only we must label it the arms, the sticky ends of the arms. Questions: what graph G can we make with DNA pieces? What is the minimal set of vertex types needed for construction of a given graph G? This minimal set of vertex types is an invariant of the graph, and it is denoted by T of G. Is a question given, you give me a graph, what is this invariant? It is an open question in general. Another graph invariant, each molecular tile can be represented as a multiset of bound types. So we put an letter to each arments, and if two arments can match together, we put a hat in the letter. So we need an alphabet to construct the graph. And what is the minimal bound alphabet? This is another question, and this is another invariant of the graph. There are new questions in the graph theory. Now, but the DNA double helix has another characteristic. One can think it about a double helix. Bless you. And this has no retention when the DNA cuts and passed. We have to the bridges of adenine, cytosine, etc. We think as oriented hybridized strands. And then this is when we come to I can say please. Well, okay. A more complex DNA structure is obtained by hybridizing and then ligating junction molecules with duplex DNA. This can be seen as gluing the strips together such that the orientation of the edges is preserved, resulting in a structure that represents a compact orientable surface with boundaries. The boundary components of such manifold represent the DNA strands of the molecule. If there is a single strand that traverses each edge twice, then the whole molecule representing a graph is a folded single circular molecule. Warning: there are graphs that cannot be constructed as a single circular DNA molecule. A simple example has two vertices with three edges. The example is in 2 slides. Don't worry. Nevertheless, for all graph G exists a thickened graph with a boundary component such that it traverses each edge of the graph at least once. This is a theorem, and it is named a reporter strand. Why reporter strands? There is such a reporter molecule or a portion of such a molecule can be then used to identify the assembled molecular structure through gel electrophoresis, perhaps combined with enzymatic approaches. This is the example, what I say. This is a trivalent graph with 2 vertices and 3 edges. Now, fatting the graph. One way is this. In this case, the boundary consists of 3 strands. I color 2 in blue and the third in red. This strand visits one edge, this other strand visits one edge, and the red strand visits 3 edges. Changing the graph. This is another trivalent graph with 2 vertices and 3 edges. Take the graph. One way is this. This thickened graph consists 3 strands. There is no reported strand. The outer strand visits only 2 edges. This inner upper strand visits 2 edges, and this lower inner strand visits 2 edges too. No one visits the 3 edges. No one strand. In this case, there is another embedding of the same theta graph, and now we have an only one strand that visits the 3 edges. This is the same thickened graph. I can say you can take the edge and twist the edge and put over, and this is the same surface. Double strand number of a graph. Given a graph G, consider all the different thickened graphs. Each thickened graph has a number of strands. What is the maximum number of boundaries of these thickened edges? A thickened graph. What's the minimum number? There are new invariants of the graph original. Example. When G is the theta graph, we have seen that the number of components of the boundary of the thickened graph can be 3 or 1. In this case, the maximum double strand number of G is 3. On the other hand, the minimum double strand number of G is 1. I come to present one operation on the trivalent graph, thickened graph. Consider the neighborhood of a trivalent vertex. I move a little the surface, another little the surface, cut and paste. I cut here the edge and paste lower, and then pull the edge, and we have this sketch. Moving the surface, so we have two options to traverse for the strands to traverse a vertex. This is one, and this is another. Replacement at a vertex. Given a graph, we have an operation between the corresponding ribbon graphs. This is called an elementary boundary operation. How does the number of components of the boundary change under such replacements? There is a theorem, but first an example. We can consider this example. There are three strands. Take a closer look at the left vertex. Make the local replacement. and check how the strands are connected now. In this case, the number of strands does not change. The lemma says the following. Let G be a trivalent graph, f of G a corresponding thickened graph. The replacement as a vertex changes the number of involved components of the boundary of the thickened graph between 1 to 1, 2 to 2, or 1 to 3. In other words, if the number of boundary curves belongs to a single component, then the number either remains unchanged or changes to 3 under the replacement. If the number is 2, then the number remains unchanged, and if the number is 3, then the number changes to 1. In the previous example, what was we at this vertex we have two strands, the blue and the red, and after the replacement, we still have two strands traversing this vertex, the red and the blue. This is the case to 2, but we will see another example the previous lemma allows us to change the connection of the boundary components of a vertex in such a way that reduces the number of boundary components. Some question? Let G be a trivalent graph and f of G a thickened graph of G. If f of G has only two boundary components, sigma 1 and sigma 2, then there is a thickened graph f hat G of G obtained from the original thickened graph by elementary boundary operations, which has two boundary components, sigma 1 hat and sigma 2 hat, such that sigma 1 hat traverses every edge of G. In fact, there is an algorithm to find a reported strand. This is from Ellingham and Ellis Monahan, and the input is a connected graph with lobes and multiple edges allowed, and the output is an orientable thickened graph with a boundary component visiting every edge. This is the reported strand. The first step is take an orientable embedding of G, choose an arbitrary face. While some edge is not in the face, choose an open edge, but incident with the vertex. Later, modify the embedding by flipping an end of the edge, and you can obtain a new face using the edge twice. And let me F the new face. In this case, consider this thickened graph of the data graph. We begin with 3 strands. Working at the left vertex now and flipping them, we obtained another thickened graph with only one boundary component. This is the case from 3 to 1. We can reduce the number of the strands on the boundary. This is the useful of the lemma. Well, there are no new questions. Can the reported strand be noted? Yes, it can be noted. This is the trefoil knot. can we assure that the output of the operations is not noted? There is a concept of edge-outer embedding. An edge-outer embedding of a graph in a given surface is an embedding of the graph such that there is a face, the outer face, that includes every edge. When we have an edge-outer embedding of a graph in a surface in the three-dimensional space, then this wall bounds a disk, and hence is noted when viewed as a curve in the space. As final remarks, many challenges arise in designing DNA molecules that are to self-assemble into a desired shape. While some of the challenges involve chemical processes, many others involve structural questions, such as which arms of the branched junction molecules should attach to which other arms, or how the route of scaffolding strand and staples through the desired structure. New mathematical formalism is being developed to solve mathematical problems arising from DNA assembly. These mathematical problems are bridges between graph theory, low-dimensional topology, and monoid algebra. Well, this is all what I'm trying for you. Thank you.
Are there any questions for the speaker?
So is it possible? Well, I didn't catch the end. If it is possible to detect whether the embedding is not unknotted, is it possible to find a way to have the unknot? But you just mentioned a theorem that that is capable to detect if that happens, but I don't know if it is always possible.
I think this is open in general, but
it's an open question. Oh.
But for example, if the case you have an outer face in this case visit all the edges and forget the surface. In this case, in the complement, there we can put a disk in the three-dimensional space, and this is unknown. But you have to consider the outer strand, not any strand. Only certain strands have this property.
Okay.
Please again the question. Number of boundaries.
Yeah, you are interested in the number of boundaries of a ribbon graph, right?
There are some theorems. I not present it, but the Janus of the surface impose an upper bound and a lower bound. This is one, and the other is the Betty number. This to make make an the genus and the Betty number give you an upper bound and a lower bound of the for the double strands.
Yeah.
This is that I can say.
Okay. Thank you.